Okay, the story is on the Western Tethys. We actually spoke about the oceans of Asia and Iran a fortnight ago, and the Alpine, and that's not a misspelling, it's not the Alps as such or Alpine, it's the whole series of mountain ranges through the western part of Europe, which have resulted from the closure of these oceans that we're about to discuss again. So there's Laurasia in the north that I was talking about, and the equator, just under the equator at 3 o'clock or 3:15 is Paleotethys, the first of these Tethyan oceans. It looks like a bit of a mouth in a skull if you take the word Laurasia as an eye. I've got a little area there outlined in white just to focus on the Atlantic, which had already opened and closed twice by this time. Isn't that extraordinary? And it has opened as a third time as the Atlantic Ocean. The two other oceans we'll discuss in future meetings or future discussions, but right now we'll just do that very quickly because we're concentrating on this mouth that's opening with a bit of an incisor sticking up from Australia. You can probably faintly see Australia written down there in the bottom, India, Australia, tacked onto Africa. This is a time when the earliest Atlantics had opened and the later ones had not really opened properly. And there's no Florida there, you'll notice, but Florida happened to be a chunk of Africa that got stuck onto USA in a later exercise. Now that's much more complicated. At the same time, I'll take a moment to look at 9 o'clock. You can see LAU for Laurentia. That's North America with Hudson Bay in it. Go down to the bottom right again and you can see India and Arabia, I wonder, within the square, at the bottom right-hand corner of the square, Africa below it. But these black lines are the lines where oceans closed at about 385 million years. So there was an ocean closing between the Atlas Mountains and the Appalachians, that's West Africa and USA or North America, Canada. That was sliding, the ocean was sliding in under the Appalachian Mountains and resulting in the mountains, hence the pink coloration. And to a certain extent, there was crushing in West Africa, which gave rise to the first of the Atlas Mountains. Similarly, Baltica was crushing against Greenland. If you can see Hudson Bay there, just east of Laurentia or below the PE. And so you had this whole mass of oceans closing. At the time, we were starting, that was giving space, you might say, for the opening of Tethyan oceans further to the east. I won't go into any detail about these because they're entire separate lectures for the closing of that Rheic Ocean, which looks a bit like the Caribbean today. Again, complex diagrams, for which I'm sorry, but it's really just to demonstrate that you had Africa with a whole series of oceans, the double lines representing the separations of new oceans. 200 million years ago, you had the first vestiges of the true Atlantic starting to form as a rift valley between Africa and North America up at the 10 or 11 o'clock position. Spain was crushed in against Tunisia or somewhere there. And that funny plate that I've outlined in red, Apulia, will get mentioned because Italy sits on that, or did sit on it. The plates do change, of course, but then the dotted one is the ocean of the expanding Tethyan Ocean. And I won't bother you with the other names, Carnix, Moisia, etc. They are sections of the crust that originally came from Gondwana in the south, but as the ocean separated, they were carried northward, a bit like India separated and carried itself northward. But ultimately, as the Tethyan plate closed by subduction of that ocean, they got crushed back again and became northern Turkey, northern Iran, Iraq, and hence are now part of the mountain chains of Central Asia. I've outlined Apulia right in the center of the diagram in red, just to keep an eye on it to see what happens to it. and you've got plate margins not dissimilar to today, a little bit younger, 20 million years later than the last one. The Atlantic had opened to a certain extent there around that red line, which is the central Atlantic. An ancestral Iceland would have sat on that far to the north, only that didn't open quite at the same time. Just to read that so that you're not rushed through things. Most of the action leading the Alpides, as we know them, leading to them, I suppose, occurred from 35 to 20 million years ago, very recently. So all this action that we sort of see going on in this diagram with a big blue fork sliding laterally in the middle of the diagram, what I call a left-hand fork, because if you put your left hand across it, you can do a sort of anti-clockwise switch with it, and that's a left-hand moving fault. The Adriatic plate, well, Apulia, we better say, was launched into the European plate. It was pushing its way north. Really, Africa was swinging around, as we'll see in a moment, and that, like a loose tooth or a particle of food in your mouth, like a cashew nut or something, it was just crushed and pushed northward over Europe, mostly in that period 35 to 20 million years ago. So relatively recently, ranges that developed. This was largely enabled by transpression. Well, that's the word, crushing and sliding at the same time between Africa and Europe. If you look at this one, it's really an image of where Africa has moved against Europe over a period of about 180 million years. It was way up in the far left corner 175 million years ago. That was the Atlas Mountain area, or the point A would be facing Gibraltar, for example. And if you follow that blue line, you'll notice it goes around into the Betic Mountains around Gibraltar. And that's the path that that section of Africa has moved over the last 175 million years. And the various outlines are the intervening periods. So if you slide down the very faint blue line from 175 million years to 80 million years, that's the position that West Africa was in at that time. And the 80 million years is shown partway down the line before you get to the arrow. And in fact, individual points like A moved along the blue line, B moved along the B to B dash line, and a yellow line is for C, and D somewhere in Tunisia, maybe getting over really towards Egypt. You have that green line marked D, and that's the arcuate movement of what I regard as a lower jaw, you might say, of that skull, meaning Africa has moved in an anti-clockwise direction over that period of 175 million years and resulted in enormous crushing, whereas the Apulia plate, which I've outlined with the blue arrow and the two red spots, was sort of shunted diagonally upwards over Europe. The words read, Africa's anti-clockwise rotation has resulted in northward displacement of its continental margin sediments into the Alps. So the Mediterranean largely closed in that time. Much of the Mediterranean or deeper Mediterranean is now gone. There's only residuals in the east. And this one I don't need to say too much, but it's an idea of the geography. At around the time, 84 million years, say when New Zealand was separating from Australia, or India was making pace across the Indian Ocean towards its collision with Asia. Here we see something of the geography. North America had big inland seas up there. We had Africa pretty much as it looks today, but two Tethyan oceans are present there, one sweeping through Europe or Central Europe. There were early signs of the Alps as a big curvilinear thing into the northeast of Spain, but a second Tethyan ocean in the south, much deeper one. People restore the geography by looking at the nature of the sediments and interpreting whether they're marine or non-marine, deep marine, shallow marine, and then work with the people who restore positions of continents, of course, and try and work out what the geography was at this interval 84 million years ago. And if you think of that on your time scale, from Sydney, you're only just getting over the Blue Mountain, somewhere towards the Jenolan Caves. If you're thinking of every kilometre being 1 million years and every millimetre 1 year. On that scale, of course, a human life is less than a handspan. It's only, well, 10 centimetres is 100 years. You can imagine how distant in time some of this geology really is if you could put it on that sort of a scale. Looking at the next one, don't know that I want to say much to that. It's the same time span presented by someone else, and you'll notice at 3 o'clock, Apulia, with a little bit of Italy way down there south of Europe. Spain sitting in a strange position relative to its current position, and you can see where the Pyrenees are today. So Spain has to slide itself westward and partially under Europe to get into the position we know it today. And the two Tethyan oceans are shown in the 2 o'clock and 4 o'clock positions there. But that Apulia plate carrying Italy is yet to push its way across Europe. I won't use that one. It's a bit too complicated, but that's actually the situation today. I will discuss it briefly. And you can see today that there are now Italy up at 11 o'clock, the Adriatic Sea marked near it, Tyrrhenian Sea separating Italy from Sardinia. The purple spots as marked are active volcanoes, and they result from the subduction that's going on in the Ionian Sea and along the eastern seaboard of Italy, and probably into the Po Plain there in the north, beyond where it reads Italy and Adriatic Sea. And then the black area up in that far top left corner are the Alpine mountains. So you can see how Italy basically has shunted up that way and resulted in the Alps. But look at those earthquake epicenters, very prominent down the Apennine range of central Italy, which is pretty old effectively because it suffered slippery sliding of this Apulia plate going northward. So the mountains are older than the Alps themselves. Where I've written at the bottom today, 0 million years. That of course just means today. But Greece and the Aegean Sea is a mass of earthquakes as it accommodates to the crunching of Africa against Europe. It's a bit like a chewing jaw, munching things up and resulting in earthquakes. Talking about resulting in earthquakes, here are today's Alpine mountain ranges, really. So you in the left, we've got the Pyrenees and the Atlas Mountains of North Africa. Then we can see the Italy with the Apennines and then the Alps to the north of them, various mountains through Croatia and Greece, which were the result of this plate sliding north towards the Alps, Carpathians, and going across south of the Black Sea into Pontiffs and Taurus Mountains of Turkey, south of the Black Sea. Did I say Carpathian for the arc at 12 o'clock on those two diagrams? Anyway, all those mountain ranges are relatively young by geology standards, less than 100 million years certainly, and most of the action much less than that as a result of the closing jaw of Africa moving in that anti-clockwise direction. Another massive earthquake, since I pinched these from the web, they're often not sharply defined. If I can't get a sharp picture by going to the original paper, I can take a tiny picture and try and enlarge it. But we can see the outline of Spain there at 9 o'clock and the Pyrenees showing with a lot of red, really shallow earthquakes. They're only perhaps down to 20 kilometres, rather like the earthquakes we get in the Adelaide Hills, Mount Barker recently. And all along the North African edge of the Atlas Mountains, the Betic Mountains of Spain, they're fairly sharp red on the southern coastline. There are some deeper ones where the subduction is occurring over at the southern tip of Italy. You see the blue colours where you must be several, at least 100 kilometres deep, 150 to 200. And of course, the plates have to be that deep, at least 100 kilometres deep, to result in the volcanoes, the active volcanoes, and the deeper earthquakes shown in purple occur, you know, in the region of Etna and Vesuvius and those things around the southwestern corner of Italy. I've just outlined crudely in white sketch where the Apulia plate has slid into Europe, and I've got another ellipse over the enormous activity of Turkey and the Anatolian fault that extends really from Istanbul eastward right through into Van, where we had an earthquake 10 or 15 million years ago that killed thousands. Bottom right on that picture is the Dead Sea rift that goes down the coastline of the Eastern Mediterranean. And I've just put a dotted line down there. It's a very sharply defined rift visible from in satellite images. Next picture, and this is a tectonic map. These effectively show when the most recent movements occurred. So the Alpine fold belt is shown in the lightest fawn cream colour. Then those of the last 10, 20 million years are shown in the green. And if it were continental crust deformed, it's shown green. And if it was oceanic crust that was perhaps disappearing, being crushed and subducted, shown in blue. And remnants of the very old Tethys ocean crust are seen in various places like the Eastern Mediterranean, that's the darker blue, the areas of the Caspian Sea out in the Far East at 3 o'clock, and the Black Sea. Some of those areas are just the final remnants of what was an enormous ocean. And they have deep sections and oceanic crust, as distinct from other sections in that, say, the Anatolian plate of Turkey, south of the Black Sea, middle section of the diagram. The only oceanic crust you see there is highly contorted and squashed into what we call ophiolite, and we discussed that last month. And they occur often in the core of mountain ranges, where a little bit of the ocean crust has been caught up in the folding mechanism. Just interesting there, the Red Sea at 5 o'clock is separating the Arabian plate, is just showing signs of opening, although it says old Tethyan oceanic crust, no way. Neogene oceanic crust, that's what it is. It's new neogene, effectively meaning new ocean crust, newly genetic, I suppose. The last, probably 20, 30 million years at most, we've seen a Red Sea develop potentially as a new ocean. It could expand if Africa were to change its movement pattern, perhaps in reverse or something. The Arabian plate may well separate well away from Africa and that become a substantial ocean. So we've been looking then at the European Alpine belt, or the Alps, specifically the Alps, I suppose. And they're relatively short in length. You know, about 1,000 kilometres is quite short for a fold mountain belt, but they're quite complex and they're relatively young and formed very rapidly and pushed up quite high. But because the rocks were not pushed down very far into the crust, the rocks indicate that it was quite a cool deformation relative to even, say, to the Eastern Adelaide Hills. You don't get much metamorphism or change of the rocks in the Alps to compare with even the areas from Kanmantoo and eastern Adelaide Hills. So it's saying east of Vienna is less than 1,000 kilometres, which is very short for a plate margin mountain range. Of course, it's high. There are 30 peaks over the 4,000 metres. Uplift has been somewhat greater or equal to erosion. The peaks are rising in millimetric terms, a few millimetres a year. Erosion's more or less keeping up with that because of the ice cover, rapid erosion by frost and so forth. They'll stay as mountain ranges for some millions of years. And of course, the Alps are younger than the Apennines. I mentioned that through the centre of Italy. Much of the uplift of the Alps is something of the order of 20 to 25 kilometres high. And that's occurred in the last 10 million years. That's really quite remarkable. Plate movements have been quite rapid, hence the complexity. There's been high pressure involved, but not necessarily great depth. So they're relatively cool. They're crushed to a third of their length. And look at a cross-section. If we go from Germany in the left-hand side across to the Po Basin of northern Italy, or about Venice or somewhere like that, or Milan maybe, how complex that is. Europe crust, or the Tethys, what was originally Tethyan ocean crust really, has slid down, and the very much altered rocks, the eclogite root so-called, they're the ones that have got into the hot zone 50 kilometres or so down. They're altered at that level, but otherwise the rocks that were probably originally deposited on the north coast of Africa are now pushed forward in the in front of this Apulian plate and crushed up and pushed over Europe into this mass of Alpine mountains. Some of the material rose up a fault and slid over the entire region. And I'll go into that a bit later. We won't try and give any detail there, but the Po Basin, very top right-hand side, you see Po Basin in the south-southeast, that's relatively undeformed, surprisingly, lying between Italy itself and the present margin of the plate, which is where it marks the Southern Alps, because there's so much faulting gone on there that a lot of the material of Africa has slid off or been pushed forward in front of it, like a bulldozer. The Po Basin is not very altered. It's subsiding gradually compared with the enormous pressures exerted upon the Alps. If we look at the bottom two diagrams, they're cross-sections, obviously, in terms of 100 kilometres depth. That's about the thickness of plates usually, and it's shown in its original form. It's 120 million years ago, yes, early Cretaceous. So it certainly was a time of dinosaurs. And we're pushing towards Sydney itself. And we go to the right-hand diagram, and here it is 120 million years later, only a third its dimension. Everything had been crushed in together by several 100%. So that's the present day normal scale cross-section. Just amazing the way that Alpine belt has been crushed. And it's not atypical for various mountain ranges throughout time, or sections of them, at least, that are more deformed. The Alps is a marvellous example, so beautifully studied by early German geologists, Austrian geologists, who've spread around the world and developed their ideas in different continents. Just looking to where all that is again, I think that it's difficult to say what the plate actually looked like in the past. Probably the blue dotted lines way out in the west of the Tyrrhenian Sea, going through Sardinia and Corsica, outline how it was at one stage, but currently it's actually limited to the area east of the Apennines. So it's really only the eastern margin of Italy now that is being pushed northward. But for example, Venice would be part of this action, being pushed and creating the Julian Alps and the Swiss Alps in the direction of the little arrow near the centre of the diagram, pushing west-northwest or something of that order. Probably at about 8, oh no, maybe not 8 centimetres a year, about 5 or 6 centimetres a year, I imagine. It's pushing its way towards Switzerland and sliding against the Dinantian Alps in Croatia and the areas east of the Adriatic Sea. Alpine mountains surrounding the Adriatic Sea, which is currently subducting under the Apennines. So there is sliding of that Adriatic plate today under the Apennine Mountains. This has presumably resulted in the Aeolian volcanic arc that's shown in a red dotted line that I've added to the diagram, starting up around Naples area, or not even that far north on my line, but swinging around through the southern portion of the Tyrrhenian Sea, which includes Vesuvius and Mount Etna, which are two volcanoes resulting from subduction of oceanic plate from the south and from the east. We get into problems often in defining the current plate. This is more or less current plate outlines, outlined in red, so that if you're looking at what's left of the Apulia plate, it's a narrow belt, the left-hand one of those two, whereas the Dinantian Alps, or the Dinarides and the Helenides, are mountain ranges, Croatia through to northern Greece. They're really acting as a separate plate today because there's a sliding force going on between that and the Adriatic Sea plate. So these things change quite rapidly. In fact, the Australian plate today appears to be changing. We've been travelling as a companion with India. India-Australian plate has usually been discussed as one plate moving together about 6 centimetres a year northward. But now it seems India is being stopped by the building of the Himalayas, and there's a separation occurring in the middle of the Indian Ocean, so that we best talk about Indian plate and Australian plate in future. Actually, there's still some indecision as to where that plate boundary is, but there's particular stress on certain belts that are considered to be the future plate boundary running through the Indian Ocean. Well, suffice to say, if we look around the top, we can see the great arc that limits the Alps and the Carpathians and the Balkans. And there's that word Moesia. I think the great vampire story comes from the Carpathian Mountains in there, Dr. Jekyll and Mr. Hyde. And that crosses the Black Sea, joins with the Pontic Mountains of northern Turkey out there at 3 o'clock. And then you've got other structures resulting in the Taurus Mountains, which is really the closing of the southern portion, Tethyan Seas, which we discussed last time. I don't think I'll do more than read to this one. Again, we've got outlines of plate boundaries there. Along the Adriatic side of Italy, the floor of the Adriatic Sea is dipping under the slab on which the Apennines have been folded by compressive forces. That's down the centre of Italy. Apennine thrusts and the Southern Alps thrust in from the north. But instead of collisional folding and compression, there is simple subsidence in the Po Valley, as indicated by the dashed red boundaries. So those east-west lines indicate a zone really where you've got resistance from Europe in the north and pressure from the Apulian plate in the south. And the Po Valley's just crumpled down a little bit. It hasn't really deformed significantly. So subsidence of the Po Valley, as indicated by the dashed red boundaries. The gradual subsidence of the Po Valley, including Venice, and the folding of the mountains of eastern Italy are related to this Apennine subduction system of central Italy. And that, of course, is the Adriatic Sea crust sliding in underneath the western section of Italy along that black line. It's effectively a geological map, and I haven't even put the key to it, so it's a little bit confusing, but it just shows you down in the bottom right corner, the Mediterranean Sea or Turanian Sea perhaps, and the Italy and the Apennines. The Po Basin is undeformed, that's that creamy to buff colour, relatively undeformed but sinking. And then this fantastic crushing that we observed that's been reduced 2/3 in overall length until you get up to Germany and France. And of course, the particularly Austrian geologists have mapped various sections which they've recognised as discrete blocks or terrains, you might say, and these represent different geological or structural portions, and that's what's showing in those colours. And the brown are the Mesozoic dolomites and limestones of the Dolomites of northeastern Italy. And then on a larger scale, we can get quite a good impression from this diagram without going into a lot of detail of that Apulian plate and the Adriatic Sea remnants today, where they've sliced their way northward, almost like the closing of the jaw of a crocodile with teeth outside it being pushed up over everything else. The Alpine European Alps are a complex mass of several small plates, including the Adriatic and Apulian plates, which were derived from Africa originally and were thrust northward over the European landmass as a result of the collision. Two peaks of this deformation are 32 to 30 million years and 21 to 15 million years. And there is that deformation, just quite staggering in concept. And those terrains, those different blocks, have all got a different history, which has carefully been studied and mapped back together, and their relative positions originally have all been, well, not all been worked out, but for the most part are worked out by European geologists. And this is really just a look at the upper section of crustal rocks that are rigid enough to move as plates, the top 100 kilometres or so, well, not even 100, where you can see the 50 kilometre mark there. Whereas the plates, normally the total section that's moving is often 100 kilometres thick. Don't think I'll go on and on about this, but that's the area, of course, that we've been discussing, Po Plain in the north of Italy and Switzerland. And here's a block diagram, simplified greatly, of that section. If you look at the bottom left, that's more or less the section we were looking at previously. Continental crust is often only 30 kilometres thick, and oceanic crust only perhaps 8 or 10 kilometres thick. But the plates that are moving go down to nearly 100 kilometres, so it's a very gradual movement over tens of kilometres that carries the more rigid upper section of the Earth, which includes both mantle or largely mantle and a variable thickness of crustal rocks. If it's oceanic, the crustal rocks are very, very thin, only 8 or so kilometres. But as it's slid up and over, it's been largely removed by erosion, and you get Klippen, a German term, sitting up on top, just little remnants of it. Or if you go further north, Austria area, you find there are windows in it that you can see through into the older terrains below. So that top layer gives you a picture of how complex it can be, because that can be occurring repeatedly over the last 20 or 30 million years, and a new layer might come across the top of that. And some even get crushed in from below. Now look over right at 9 o'clock is the Mont Blanc sitting out there, and somewhere in that region also there'd be the Matterhorn, possibly best placed on a Klippen, one of these fragments of the Apennine plate crust, or some of African crust, and we'll have a look at that in a moment. The Matterhorn has been shown with a star right in the centre of the diagram near the little Klippen, and in fact, a portion of it is the clipping. So if you've got a concept of all this stuff crushed together and remembering that it's a third the size, if you pull both edges of this block diagram apart this way, then you would, and you'd have to pull it apart to 3 times its size and be able to restore each of these sections back in their original paleogeographic positions. And that clipping would go back to the continental margin of Africa. This is the Matterhorn, and the lower portion is a portion of that Tethys ocean material, but it was sediment that had come off Europe, meaning the sedimentary margin of Europe in the north, whereas the upper section above the yellow line is part of this Apulian plate and regarded as a microcontinent that was originally attached to Africa. And it has been pushed right across the top, and it's sitting there as a clipping, effectively eroded by the ice into this distinctive form that the Matterhorn offers. This is a view of the Matterhorn showing the upper crustal material of the Apulian plate that was originally an exotic block from Africa. We use that word exotic to mean it's far away from where it ought to be. It's quite exotic. It has been thrust over the Tethyan sediments of the European margin and translated several hundred kilometres northward during ocean closure, which was at its peak about 20 million years ago. So this is a relatively young section of the Alpine movement. And of course, it's just a residual on the very crown of the Alps. So there again is that Adriatic plate that's been crushed northward. And the red dashed lines are effectively, you might say, the best estimate of a boundary of Eurasia as against a boundary of Africa. There's so much complication in the intervening zones, like in Spain at 3 o'clock, Anatolia. It's just a history of closure of one point of another, one ocean or another. And the Tyrrhenian Sea is a very complex, relatively new ocean, rather like the Caribbean, that's crept in a complex way from Africa and Spain's join across the Gibraltar Straits. And someday or other we might discuss that in more detail. But if you took a given point within the red lines, you'd be hard pressed to say, oh, well, that's the Eurasian plate, that's the African plate. They're really microplates that are all crushed between the great jaws of Africa and Eurasia. Eurasia being the current plate, which is one huge continental plate, the only oceanic material really being westerly of Europe to Iceland, or the centre of the Atlantic Ocean. And that's new ocean of the last 80 million years. So that the plate has been, or is, and has been coherent mass of continent extending from China through to Great Britain. Red dot lines are respective margins of the Eurasian African plates as we know them today. Between them is a crush of platelets that are undergoing compression as a result of the collision of the larger masses. And now I'm coming, we've got Greece outlined there at 11 o'clock up at the top, coming down halfway down the diagram, and then the dark mass of Turkey on the other side of the Aegean Sea, a little obscured by my writing. I've written Mediterranean accretionary wedge. Now, an accretionary wedge is you might say, the huge delta of sediments that occurs when there is subduction. Obviously, seafloor sediments get scraped off by the subducting oceanic crust as it slides in under the continent. You get an accretion of debris and sediment and so forth, plus you get all the material that's coming off either a volcanic range or a mountain range that's crumpled up by this process of subduction. And you get an enormous wedge of sediment and other material. So the Mediterranean accretionary wedge is believed to have a core of thick salt deposits, which formed at the time the Mediterranean dried up. A number of times it dried up in that period of 6-7 million years ago, even probably a bit later than that. I think 5.7 million years ago, the Mediterranean was effectively dry. And then it filled again, rushing torrents coming in from the Atlantic as sea level rose or tectonics allowed a gap. It flushed into flood the Mediterranean again. This happened so often that you've got almost a kilometre of salt deposited in certain areas, particularly south of this diagram in the eastern and southeastern portion of the Mediterranean. Anyway, you have the sea plate of the Aegean in the north sliding under more sea plate of the old Tethyan Ocean, effectively, in a series of subductions. And then Africa also, or the oceanic crust associated with the North African plate, is also sliding northward. So you've got this Mediterranean ridge accretionary complex, everything jumbled up in there as a result of double subductions facing one another. You've got volcanic arcs that are residuals from ancient subduction belts, or possibly still from the African plate. The active plate includes Santorini, which had a huge eruption, probably one of the biggest in history or prehistory, but it is probably that wiped out one of the early civilizations of Crete and Rhodes, who were supplying copper to Egypt at the time. And that's when Egypt lost many of its metallic skills because it no longer got sources of copper to make its bronze. Anyway, you can see there's a mess going on there with those yellow triangles pointing at one another, indicating that there's opposed subduction in that zone. And it's believed also there's a very big ridge of salt resulting in there, which is going to have, or does have, some extraordinary effects on the ocean floor. What can I say there? You've got two arcs, one island arc, which is no longer volcanic, whereas the northern one is still quite active, with the Santorini as its prominent example. One boundary suggested for the Eurasian plate and the African plate is this blue line, but I think you can take your pick in a way. It's just that there's a lot of activity going on subsea and across the Greek peninsula that account for earthquakes across this belt, shown in blue dashed lines. I've put that in actually, but you can see up in the 2 o'clock position where it says Alexandria or the island of Marina, you've got a belt of a very deep ocean floor, and that certainly continues as a major fault boundary running easterly across Turkey, and is a prominent boundary for sliding fault. 2020 a magnitude 7 earthquake in the Aegean Sea ripped through the province of Western Turkey, causing widespread damage to Izmir, the country's third largest city. And reading on, immediately following the earthquake, a tsunami damaged parts of the coastline, 116 people killed and over 1,000 injured. That's 2020. I could probably get more recent ones actually, but this is an old slide of mine. According to Turkey's disaster response group, more than 4,000 families lost their homes as a result of tsunami. Well, the whole region of the Aegean is subject to earthquakes, of course. The Great Alpine Belt extends from the Pyrenees to the Himalayan mountains. It was formed during the last 60 million years as the African plate began to collide with the Eurasian. Today, the Turkey plate or Anatolian plate escapes towards the west. It's a bit like a squeezed lemon pip. It's going westward or southwestward along very prominent faults on either side. It's just trying to escape from this pressure exerted by the closing jaw of Africa against Eurasia in the north. The very movement that has closed those Tethyan oceans. And the North Anatolian Fault running through Tehran and across through the North Turkey and south of the Black Sea, it forms the present-day plate boundary with Eurasia and runs through northern Turkey. In Iraq and Iran, the Arabian Plate is pushing north, resulting in the Zagros Mountains that run up from almost Afghanistan up through Iraq and finally towards Turkey. There's Turkey and the Black Sea with actually, you can see how deeply it's presented there. If you look very carefully in the center of the diagram, you can see contour belts going down to significant depth in the center. Once the shallow blue areas were not flooded, I say once, if you were to go back 10,000 years ago in a cold period when most of the waters of Earth were stacked up as continental ice sheets in northern Europe, then all those blue, lighter blue areas were dry, and probably some of the deeper zones as well. Hence, there's an enormous amount of archaeology lost there in Ukraine, Danube Delta area, and so forth, where man must have settled in early agriculture, etc. Here we have that major fault running across from the Sea of Marmion in the west, or from the Aegean Sea through the Sea of Marmion, just south of the lobe of the Black Sea, the western lobe of the Black Sea. That's a triple yellow fault there, running almost through Istanbul, which is not marked, and sweeping across, it passed through Tehran, going across Vam, etc., in the Far East, and joining up with other fold belts that, or fault zones that have resulted in fold belts of the Zagros Mountains of Iraq, Iran, I've got to say in that order. Well, look at the faulting systems throughout that volcanic arc in the southern Aegean and along the east-west fault, Anatolian fault through Turkey, picking up in the Zagros at 4 o'clock, etc., etc. Just reading that one, earthquake epicenters and plate movements where Europe meets Asia. The Hellenic arc is clearly a structure of great instability today. That's in the west. It's down, extending into the Mediterranean. It's under the pressure from Turkey, which is essentially a pip sliding west like that green arrow in the middle of the picture. And we'll come back to shared screen or to unshared screen or whatever we're doing and discuss. Anyone got a question for me, or have I put you all to sleep?